So one of the things that we're going to use quite a bit is this idea of fugacity. And so fugacity hopefully is not a new concept, something you've seen before from thermodynamics courses, but oftentimes it's something that is still a little bit confusing at this point. And generally, we're still working on trying to figure out what fugacity really means, right? A lot of times we hear fugacity described as this sort of fudge factor that deals with the fact that the world is not necessarily ideal. And while at perhaps some level that's not completely inaccurate, one of the things I'd like to do is try to push us a little bit more to recognizing that fugacity is this intermediate that helps us to connect the idea of chemical potential to measurables. And one of the steps that we're going to take to try to sort that out is to go through and talk a little bit about where fugacity actually came from. And so we're going to talk about the work of Lewis and how ultimately Lewis came through and defined fugacity in a way that makes that connection to chemical potential. And then separately, we'll come back and talk about how we take the next step further in the other direction in terms of connecting fugacity to measurables. And so in terms of thinking about the Lewis definition of fugacity, we're going to start with the ideal gas mixture. And so we're going to think about an ideal gas mixture, and we're going to do that in terms of the Gibbs free energy. So we'll start out with G. We'll use the superscript IgM to indicate ideal gas mixture. And we'll use the nomenclature that we have in the Matsoukas text. And so we're expecting that the Gibbs free energy will depend on temperature and pressure. And because we're dealing with a mixture, we're going to have some compositional term. We'll use the curly brackets here to indicate that we might have multiple values of the mole fraction, just depending on how many different components we had in this mixture. We'll use X here. We're talking about an ideal gas mixture, and in a lot of this course, we'll be using Y for mole fractions of gases. Doing that to be consistent with the nomenclature that you're going to see in Chapter 9 of Matsoukas, but just recognize that this X here is just mole fraction, and it could just as easily be listed as Y. So we know that for the second law properties like the Gibbs free energy, we can write out the ideal gas mixture expression in terms of two terms. The first term is going to be a summation over all the components in the mixture. And that's going to be the mole fraction weighted sum of the Gibbs free energies of each pure component. Right? And so we can write that out as the mole fraction times the Gibbs free energy. Again, we're dealing with ideal gases, but now in this case, it's not a mixture property. We're thinking about each Gibbs free energy of each component in the system. And so we'll denote that here as pure I. And because we're dealing with the Gibbs free energy of just a pure ideal gas, that only depends on temperature and pressure. Okay, whereas the ideal gas mixture Gibbs free energy has that compositional component due to the fact that that's looking at an actual mixture. And then, again, because this is a second law property, we have to deal with entropy. And so we have an additional term that tacks on here, RT times the sum over all components in the mixture of Xi ln Xi. Right, and so, if we think a little bit more about these terms, right, this latter term here is the entropy of mixing term. And again, we have the mole fraction weighted sum of the Gibbs free energies for each component. And so this is what you find if you go into the Matsukas text and look at table 9-1. You can see this relationship shows up there. Again, nomenclature is a little bit different. We're trying to be a little bit more explicit here in how we write out things in terms of emphasizing the mixture versus non-mixture components of things here. But ultimately, at the end of the day, this is what we're thinking about as we start to look at the ideal gas mixture in terms of the Gibbs free energy of the system. And you can see how the entropy of mixing term enters in, whereas the first law properties, things like volume, enthalpy, and internal energy, simply don't have that entropy term. And that's a key distinction there between what we call the second law properties, like entropy and Gibbs free energy, compared to the first law properties. All right, so we've got this expression for the Gibbs free energy of the ideal gas mixture. This is just what we expect to be true for this system, and so it's a great starting point here. We know from our other discussions that if we apply the partial molar operator to the Gibbs free energy for this ideal gas mixture, that will allow us to define by definition the chemical potential. And so we could come in and say that the partial derivative of G of the ideal gas mixture with respect to some number of moles of component I, if we do that at constant temperature, pressure, and number of moles of everything else that's not component I in this case, right? This by definition is now the chemical potential of component I in the ideal gas mixture, right? And this carries through as a function of temperature, pressure, and still composition. All right, so that's by definition, and we know we can always come in anytime we take this partial molar operator on the Gibbs free energy in any form. That's going to get us to that particular form of the chemical potential. And if we think about taking this further and applying it to then the right-hand side of the equation that we have up here at the top, we see that then this chemical potential could be expressed as the pure component I Gibbs free energy, function of temperature and pressure, and apply that derivative as well to the entropy of mixing term, and we get something that looks like this. And so when we go through and hold all of those nj's not equal to I constant, that helps us out with the summations. We take that derivative, and if we clean things up a bit, this is what we get. And this is Matsukas, I believe, equation 9.37 at this point. All right, so now we've got a situation here where we're looking at an expression for the chemical potential of the ideal gas mixture, and we're making some progress there. Now, what Lewis did next was to say we're going to consider a particular temperature T, and so we'll indicate that here, that moving forward, we'll be fixing the temperature. And that's fine for our purposes of moving forward with the derivation. So if we fix the temperature and say we're going to just think about some particular temperature of the system, which is going to be fine for our equilibrium approach to things, right? Because oftentimes we're saying we're considering equilibrium at some fixed temperature, so that's okay by us. What we can do is go through and take a differential of this ideal gas mixture chemical potential, and we can do that at fixed temperature. And so we could say, and this is similar to taking our total differentials, that d ui ideal gas mixture, I'm going to drop the temperature, pressure, and composition dependence here. The temperature dependence is going to go away since we fix at a constant temperature. But we can set up this total differential, and so we get the pure component I ideal gas Gibbs free energy. Take that derivative with respect to pressure at constant temperature, and we've got the dP out here to finish off the total differential. And we can go through and do the same thing with the entropy of mixing term. And so in this case, we'll end up with a situation where RT d ln xi, this fixing temperature and taking that derivative doesn't affect that term, but we've got our total differential here set up for our entropy of mixing term. All right, so now we've got this partial derivative that's showing up here in the expression. And much like we would do for other total differentials, we want to try to relate that to something that looks a little bit cleaner than just a differential as we have here. If we think about this situation, right, we have an ideal gas and a pure component. And so we can do some work on this derivative by thinking about the fact that our fundamental equation for Gibbs free energy is dg is equal to vdp minus sdt. And so if we think about that, right, that's a situation where we can take that fundamental equation, which we know is always true, and we can take the derivative of g with respect to pressure at constant temperature, and that ends up giving us then the volume, or the molar volume of the system. And so we know that this partial derivative of Gibbs free energy with respect to pressure at constant temperature is going to simply be related to the molar volume of the system. And in this case, we're just going to have the molar volume of pure component I as an ideal gas, as that is what we're specifying for this Gibbs free energy. And so this is going to be equal to the molar volume for the ideal gas for pure component I. And if we think about this, right, we know what the molar volume is of a pure component ideal gas, right? The ideal gas law tells us that this is just simply equal to RT divided by P, right? And we can do that because we're dealing with the ideal gas, right? And so we can simplify that a good bit here. And so we end up then with a situation where our total differential expression, still for the chemical potential of component I in the ideal gas mixture, now is equal to RT divided by P dP plus RT d ln xi. And again, xi, the mole fraction here of the gas. And so we can get everything in terms of differentials of natural logs, which is going to help us out. This is equal to RT, and then we lump everything together. We get the pressure term as d ln P plus d ln xi. And that's going to come through and end up resulting in a situation where our chemical potential of component I in the ideal gas mixture, let's just rewrite that out here, d mu I, ideal gas mixture, is equal to RT d ln xip. All right, so for a fixed temperature, right, this is just how we relate ultimately the chemical potential of component I in the ideal gas mixture to what ends up being that temperature that we fixed, and what is the partial pressure of that gas in the ideal gas mixture. Right, so we have a relatively straightforward relationship here between chemical potential and the partial pressure of the gas, again, in the situation where we have this ideal gas mixture. And so what Lewis recognized was that this structure is fundamental in nature, but it only applies to the ideal gas system. And so Lewis said, well, what if we take this same structure and now just expand it to deal with situations where things are not ideal, right? And so I usually would come in and draw a line through here and basically say at this point, the derivation experiences a discontinuity, right? Lewis is going to come in and say, now I want to say that the differential of the chemical potential of some component I in a real mixture, so we're not limited to the ideal gas mixture, is going to be defined as RT d natural log of something we're going to call the fugacity, right? And so this is a definition. This does not follow from the previous line in the sense of a derivation where we can make assumptions or mathematical manipulations, right? This is Lewis saying, I am going to define the fugacity relative to the chemical potential using the same mathematical form that we get for the ideal gas mixture. And that's convenient because now his definition of fugacity converges in the limit of an ideal gas to exactly what we would expect for an ideal gas. And so there's a certain level of clarity or cleanness associated with the way that Lewis approached this. And one of the ways that we could look at that is to say that in the limit where pressure goes to zero, or where we reach the ideal gas limit, the fugacity of component I becomes the fugacity of component I in the ideal gas mixture, and that we see is simply equal to XIP, or the partial pressure of gas I in the ideal gas mixture. All right, and so we're familiar with that, right? We've heard about Raoult's law. We've talked about this idea that we tend to think of the partial pressure of the ideal gas as being equivalent to the fugacity. We've probably talked about that in previous thermodynamics courses, and that's still preserved with Lewis's definition. But now, in Lewis's way of defining fugacity related to chemical potential for any mixture that we want to think about, it gives us the ability to use that same functional form between chemical potential and fugacity. And that's, again, going to be an intermediate for us to get in between measurable things down here in the real world and chemical potential up in the world of abstraction, where we can apply our thermodynamic equilibrium criteria of saying that the chemical potential of any given component must be equivalent in all phases that are in equilibrium with one another. And it's making, as Prausnitz said, it's making that jump between the real world and the abstract world that's quite difficult. And fugacity gets us sort of one step closer to making that jump. Again, I like to point this out because in some ways this idea of a fudge factor is not completely inaccurate, because Lewis just came in and said, I'm going to define it this way. But at the same time, there's a little bit more to it in terms of the connection to chemical potential and the way that Lewis chose to set up the fugacity and connect it up to the chemical potential and the mathematical form that was used here to do that. We can also see, and you've read about it in Prausnitz as well, right, that what then becomes a natural progression here is this idea that the fugacity of any particular system can be expressed as the mole fraction times some fugacity coefficient times the pressure. And this could be true for a gas, it could be true for a liquid, it could be true for a solid, right? We can always define the fugacity as this xi times p multiplied then by a fugacity coefficient that is sort of the fudging, if you will, that makes the connection here. But what that means is that the fugacity coefficient in this case, and thus the fugacity of a real or non-ideal system, carries with it all of the information that's important about the system for describing that non-ideality. Remember, chemical potential is telling us how the Gibbs free energy changes in the system when we put one more molecule or make an infinitesimal change in the number of moles of a particular component. Right? That's the core essence of chemical potential as given by this partial molar operator applied to the Gibbs free energy. So in that chemical potential, we're seeing everything about how the energy of the system changes when you make a subtle perturbation of how many moles or the composition of the system in terms of a particular component. it's giving you that information. So any non-ideality that's in there is baked into the fugacity. It's baked into the fugacity coefficient. Later, when we talk about activity coefficients, it's baked in there as well. And so it's helpful for us to understand that fugacity is this connection between chemical potential and measurables. It's an intermediate. We still need to do a little bit more to get the whole way there, but this gets us on the road to trying to understand ultimately that connection. And so we'll go ahead and wrap up Lewis's definition of fugacity relative to chemical potential here.